My name is Abel Leyva. With the help of my teammates Carlos Rodriguez, Roberto Robles, Esteban Ríos, and Juan Guerrero, we will present our heat sink design and explain how and why we achieved our final product. A heat sink is a thermally conductive component added into systems to dissipate heat more efficiently. And in this case, our job is to design a heat sink that increases the heat transfer while it also effectively cools the component. In this project, we were given specific restraints regarding the material and size it should be composed of that our design must meet and will certainly affect the final product. The objective of this project will be to understand the relationships between the physical characteristics of a heat sink with the variables in Newton's laws of cooling. To accomplish this goal, we will be using formulas that we've learned in class and the software Fusion 360 that allows us to design and simulate a 3D design of the heatsink. With all that being said, we would like to further explain the formulas involved.
My name is Carlos Rodriguez. I'll be presenting on the theory for our project. So the theory can be divided into 3 steps essentially. Step 1 being the manner how we can relate heat transfer to certain variables found in our heatsink design process. So we found this most evidently in Newton's law of cooling, which equates heat transfer to variables H, A, and delta T. So first thing to note, delta T isn't something we can manipulate, as it is described by the base temperature of our heatsink, which is already given and not something we can change, and the ambient temperature, which is something that we don't want to have heat transfer depend on. So the 2 variables that we will be manipulating is H and A. So let's start with H. The H is the convective heat transfer coefficient, which is the factor that describes the thermal resistance between the heatsink and the fluid medium, which in our case is the air flowing through the fins. This variable plays into the concept that as air heats between the fins due to convective heat transfer, it becomes less dense and rises, cooling the heatsink. Additionally, by increasing the area via the addition of fins, the heat emitting from the electrical component from the bottom can be dissipated more effectively. This is the A variable. And this is kind of analogous to how a car radiator divides water into a lot of streams in order to cool it quicker, right? So that the heat transfer is increased. So this is along the same lines of that. Now for step 2 of our theory process is defining all the relationships that will be required to solve for heat transfer. You see, H and A are both variables that are dependent on other relationships found in our design process. You see, things like Nusselt's number as well as Rayleigh's number are values that will need to be found before solving for heat transfer. Additionally, we also want to use Newton's law of cooling simply as a base equation, but instead find a certain derivation that describes our case a little more accurately. For example, initially we wanted to use the infinitely long fin case equation to describe our situation. However, this does not take into consideration the desired fin tip temperature. We did find that another case that specifies the fin tip temperature was required in order to solve for heat transfer. Finally, step 3 to our theory process is putting all of these relationships together and seeing what values change what. For example, how the dimensions of our fin length will affect the heat transfer, as well as the spacing between the fins, how that will affect heat transfer. Not only that, but we will also include the fin efficiency equation to also make better conclusions on our design. So that's the theory to our project.
Hello, my name is Roberto Robles, and I'll be explaining the code part of the MATLAB script for this heat transfer project. At the very top, you have LF, which is the fin length, which will be our input for the function. This is how we were able to get the graphs and compare them and use them to find the number of fins, to find how much heat transfer we get, and more importantly, to guess as little as we could. First of all, you can see the first graph plots heat transfer with the length in centimeters, heat transfer in kilowatts. Second one, fit efficiency and the length. The third one is the number of fins and the heat transfer. That way you could relate it to the first one and to the second one and find the most efficient part. Then we arrive to the function. Here, as I mentioned before, the input is the length of the fin. This length is an array ranging from 0.005 meters, which is just 5 millimeters, goes up to 5 centimeters. This is in increments of 1 millimeter each. After that, we are listing variables such as length, width, thickness, the surroundings, temperature of surroundings, temperature of the surface, temperature of the tip of the length of the fin, which is 65 specified by the project. And then with those, we find the corrected length with the length and the thickness. That corrected length is used to simplify equations. Then we have also the temperature of the film, which is used to find properties of the air and things we're going to use. With that, after that, we use more formulas to find the perimeter, the cross-sectional area, also using the corrected length, which is really important there. After we find beta, the problem number from the table, the viscosity from the table, which are just constants here that are used for further formulas. Afterwards, we find the radius number, which is given by that formula specified in the project. Then, with that, we can find this optimal spacing for each fin. With that optimal space of each fin, we're able to find the number of fins that we could use. That's where our graph comes in to place. After, with that same optimal space, we can find the H, the heat transfer, which again will be an array due to the different lengths. Then we have our M, which is given by that formula, and ML, which is useful for finding the efficiency of the fins and also the heat transfer of the fins. That heat transfer is given, as I said before, by a different formula, since we are using a specified temperature at the fin tip. Thank you. That was all by my part.
And for my group's project, I was in charge of the CAD design simulation portion of it. So the biggest hurdle we had to overcome with the project as a whole was getting the length, because we also wanted our fin lengths to meet the infinite fin requirements. But after Roberto created his MATLAB code and ran all the numbers, we were able to get those values. So once I got the dimensions, it was just a matter of designing it. So the software I used was Siemens NX. So I designed it in Siemens, and then I used the SimCenter Thermal Flow solver to do the analysis. So when I was doing the analysis, the first problem I had was that they didn't have the exact material we used in our calculations, which was aluminum 1100. So it was easily solvable. I just created a separate material file for that and assigned it to the part. Secondly, I assigned a constraint of convection to the environment, with the environment ambient temperature being 25 degrees C, or room temperature, which is what we use for our project. And the convection coefficient was the one that Roberto got from his calculations. And then when it came to assigning the load, this is where I had the most trouble, because it's really strict with what you can do to assign a load. So using this equation that you see right here, I was able to kind of get wattage that was around the load that would take the bottom of the heatsink to be from 0 to 85 degrees C. From that point, I just applied the load, which you can see right here, which is 225.34 watts. And then I just solved it. So you can see the results right here. It's more of a thermal gradient, but I wasn't able to put the initial conditions of the bottom of the plate being 85 degrees C. However, it gave us a good idea of how our heatsink would work.
Hello, my name is Juan Guerrero, and I'll be doing the conclusion. Our simulation is the final indication in designing a successful heatsink. Once our calculations had been made using Roberto's MATLAB code, we were able to choose dimensions. As he went over in part of the presentation, his code allowed us to be more effective with our decisions, as it allowed us to manipulate the numbers without having to redo the calculations by hand each time. And this allowed us to choose the dimensions that ensured optimal heat transfer. With this, we were able to translate these findings and design and then simulate the heatsink using computer-aided design, CAD. That, of course, was done by Esteban, and as he went over, and seen in the figure above, the temperature dissipates as soon as it travels to the fins. Notably, the base of the heatsink experiences the most amount of heat. This is due to the less efficient heat transfer it contains. These findings concur with the calculations done with Roberto's program, as well as the theory done by Carlos, and the addition of the fins do aid in the heat transfer process and effectively cool the component at a more effective rate. And that concludes our presentation for this heat transfer project.